Hello, we are Team Alan Turing. We are going to present our final project, PulseNet, a distributed health alert system. The problem we are solving is the fragile nature of real time health monitoring. When a patient's heart rate spikes, the system must process that anomaly and alert a doctor instantly. However, if 100,000 patients' devices sync at the same moment, traditional systems crash under the load or databases get deadlocked. In healthcare, a dropped message or a delayed alert can be fatal. We needed a system that guarantees fault tolerance, handles massive concurrency, and processes streams in real time. This is our architecture diagram. Looking at related systems, traditional electronic health record systems often rely on batch processing or simple client server polling. When apps have to constantly ask the server if there's an emergency, it wastes bandwidth and introduces latency. Other modern systems use Apache Kafka for streaming, but maintaining a dedicated Kafka cluster is expensive and requires manual scaling. Instead, we choose a 100% serverless, event driven AWS architecture using SQS and WebSockets to push data instantly without maintaining servers.
To solve these distributed challenges, we made four key design choices. We used decoupling for load balancing by placing an Amazon SQS FIFO queue between our data ingestion and our anomaly processing. If ingestion spikes, the queue buffers the messages, preventing our business logic from crashing. To handle at least once delivery, distributed message queues often accidentally deliver duplicate messages. We designed our system to be idempotent. By using a unique alert ID as the sort key in DynamoDB, our database safely overwrites duplicate alerts instead of paging the doctor twice. To avoid hammering our database with read requests on every single heartbeat, we implemented an in-process warm cache at the compute layer to hold patient thresholds. So when the Lambda fetches patient A's personal threshold from DynamoDB, it stores them directly in the Lambda container's local memory for the 5 minutes. For the next 5 minutes, every heartbeat from patient A is evaluated against their personal limits in sub-millisecond without ever making a network call to the database. About fault tolerance, we implemented dead letter queues to catch failed messages so data is never silently dropped. We will show this by simulating a crash in the server later in the demo. Now moving on to the code walkthrough. Let's look at how we implemented the caching layer in our anomaly detection component. This Python code runs on AWS Lambda. On line 29, you can see we declared a global dictionary called threshold cache. And also you can see the 5 minutes cache storage because AWS Lambda execution environments stay warm for a few minutes after they are invoked. We can reuse this global state across multiple heartbeats. In our get threshold function, we first check if the patient's data is in memory. If the memory is there, we have a cache hit and return it instantly. If not, we have a cache miss. Fetch it from DynamoDB and store it in the next heartbeat. This completely removes the database read bottleneck.
Now we are going to be seeing the live demo. You have seen the architecture, the device, the cloud, the clinician. Now I want to show you the patient experience and the clinician experience. Same code base, two completely different worlds. Let's start with the patient. This is the patient side, where first thing worth calling out, there is no password here. The phone itself is the identity. We provisioned an X.509 certificate on the device at registration, and AWS IoT Core trusts that certificate. So when this phone connects, the cloud already knows it's patient P001. Now I'm going to be signing in with P001. The ID field is for human convenience. It lets me pick which patient profile this build is acting as. The real authentication is happening at the TLS layer, not here. At the home screen, top right, we have a green live build. That means we have an active MQTT connection over TLS to AWS IoT Core, not a heartbeat to a status endpoint, an actual open session ready to publish. Seeing the buffer batch under the patient row, this small batch next to the patient row is the local buffer count. If the network drops, every reading we generate goes into a bounded ring buffer on the device, capped at 500 entries, FIFO eviction. When the connection comes back, the buffer drains in chronological order before we resume live publish. Nothing gets stopped, nothing gets reordered. Moving to the heart rate and SpO2 cards, heart rate and oxygen saturation pulled from Apple Watch through HealthKit. Here's the interesting problem. Apple Watch does not stream heart rate. It samples in batches, anywhere from every 5 seconds when you're active to once a minute when you're at rest. If we just polled HealthKit every second and called it good, the UI would freeze for long stretches. So we decoupled the UI cadence from the published cadence. The app pulls a fresh 60-second window from HealthKit every 15 seconds and renders the most recent sample. Then, independently, every 30 seconds, we publish to MQTT. One loop for the user, one for the cloud. They don't block each other. Seeing the tiny diagnostic which shows last sample, poll equal to 15 seconds, last publish equal to 30 seconds, and attempts equal to n. This line right here is the observability of for that. Last sample time, poll interval, last publish time, publish interval, and attempt count. If publish is stopped, you see it immediately. We don't hide failure behind a green check mark. This strip is internal diagnostics. Query counts, observer state, whether we are getting push samples or polling. You wouldn't ship this to a patient for the demo. It's the evidence layer. Seeing the system health, every external dependency this app touches has its own row with the last successful timestamp and the current state, MQTT, local buffer, HealthKit permissions, and the clinician backend. If any of these is yellow, the app is being upfront about a degraded condition. Yellow is honest. A fake green is a bug. In a distributed system, you don't get to pretend everything is fine. You tell the user what you actually know. Now the part I have been waiting for, fault injection. So now what I'm going to be doing is I'm going to be injecting a HR spike which is above the patient's threshold. I just injected a heart rate above this patient's threshold of 130. That reading flows through exact same path as a real high reading. Published to MQTT, validated by Lambda, queued in SQS, evaluated by the anomaly Lambda, dispatched as an alert. No special path for synthetic data. Same code, same pipeline. Now I'm going to be going into the clinician to show more about how we have triggered it and how to see the particular data from the clinician dashboard. I'm going to be logging in. So we have 3 tabs in the clinician dashboard: patients, alerts, topology. Patients, everyone we are monitoring. Alerts, real-time alerts, feedback over WebSocket, push from AWS, not polled. And topology, a small visualization of the system so the clinician can see which components are healthy. And also we have made sure that we can simulate the raft consensus algorithm to show you how leader-based election works on AWS multi-AZ in the DynamoDB. So you can see from the previous thing that an alert is triggered, which we have triggered previously. So which we have done it through the anomaly detection. And now I'm going to be showing how to kill a leader. Once I kill a leader, another follower becomes a candidate and is voted as a leader, and the previous leader goes offline. When the previous leader comes back online, it's going to join as a follower. Just this shows how the raft consensus work in the DynamoDB. Coming to the patient detail, now we have all the patients which are listed under a particular clinician, and I have made sure that I have logged into demo patient 1, and this is where we have connected with the Apple Watch. Once I click into the patient P001, I'm going to be seeing their HR, which show also it shows the 1 hour chart. The chart is the last hour of vitals queried from DynamoDB with the bounded time window, not a full table scan. This matters at scale. If a clinician has 100 patients, none of these queries can be bounded. When the clinician needs more history, this drawer pulls the last 24 hours newest first with the exact fetch time. Okay, so if the backend is slow or behind, the staleness is visible, not hidden. So here you can see that the 175 is the anomaly which we triggered in the patient side, which is noted and also sent as an alert to the patient. When I click refresh, refresh is idempotent. Tap it once, tap it 5 times, same result. No duplicate state, no race conditions, standard distributed systems hygiene. So this is our clinician app. Here we can see the alerts which are listed from the clinician, and also we can see the system health, how it works with the AWS. And as I mentioned about before, it's the topology over here, which shows the demo of how the DynamoDB consensus algorithm works, and this is for the demo. So that's the mobile layer. 4 things I want you to take away. certificate based identity, no shared secrets on the device, local durability, 500 reading buffer with ordered drain, honest observability, every state visible, no green when yellow, and one code base serving two completely different user experience. The cloud side, what happens when these readings actually reach AWS, how anomalies are detected, how alerts fan out, how everything is logged for audit. That's gonna be continued now.
Now, let's demo a key aspect of our project, reliability under failure. First, I'll send a normal healthy heartbeat through the terminal. It processes success into storage, but no alert fires on the doctor's WebSocket dashboard. But what happens if a device malfunctions and sends a corrupted payload? If a payload is missing a critical piece of data like patient ID, it will crash our anomaly lambda. I've just injected a poison pill, a corrupted payload, into the processing queue. The lambda tries to process it and it crashes. Because of a fault tolerant design, SQS intercepts the crash. It automatically retries processing the message 3 times. When it fails the 3rd time, it strips it from the main queue and drops it in the dead letter queue. So now let's go into the DLF FIFO. As you can see here in the AWS console, the message is safely quarantined in the DL queue. We can see the count is now 10. So the system did not crash. Other patients are still being monitored perfectly. And this corrupted data wasn't lost. It was waiting for an engineer to debug it. Evaluating our design, the impact of these choices is massive. By utilizing the in-memory cache, we reduce database reads by over 90% during high-frequency ingestion, massively reducing latency. By using WebSocket push technology instead of polling, the latency from patients' heartbeat spiking to the alert appearing on clinician screen across the country is constantly under 1 second. And through our SQS DLQ setup, we achieve a high available system that guarantees zero silent data drops. To summarize, PulseNet successfully solves the challenge of real-time health monitoring. We moved away from fragile systems and built an event-driven system. We secured the edge with MTLS. We decoupled logic with SQS to handle load spikes. We solved duplicate deliveries with idempotent database keys, and we proved our reliability by gracefully catching system crashes under dead letter queues. Thank you for your time.